Okay, so maybe we get going. Thank you, everybody, for coming to our seminar. Today we have Yuansi Chen who's an assistant professor at the Department of Statistical Science at Duke University. He did his postdoc at ETH, where he and I overlapped for about a year and a half. And before that, he obtained his PhD at Berkeley in the Department of Statistics. And before that, he was in France at École Polytechnique, where he and Zaid overlapped a bit. So Yuansi's main research includes Markov chain Monte Carlo algorithms, convergence guarantees and high-dimensional statistical models, high-dimensional convex geometry, domain adaptation, and statistical challenges that arise in computational neuroscience. Today, he'll talk about localization schemes and their connections to MCMC. And a little bit of personal note, what I'm often very impressed with Yuansi is his ability to work on both applied and very theoretical projects. So he's done very interesting things in neuroscience. On the other end of the spectrum, he's basically solved a open conjecture. And so he's able to kind of do all of those all together in a very amazing way. And he's also a wonderful friend and colleague. And I will pass it to Zaid for a double introduction.
Thank you. Yeah, so it's a delight to welcome Yuansi after many years. So Yuansi did his master thesis with me and Julian Meral many years ago, was it like six or 7 years?
Yeah, more than that. Yes, yeah. 7 years ago. Yeah.
And I just wanted to share some memories. So Yuansi came, we had a project for him on a method Leo Breiman called archetypal analysis. So it's a method that is described in a few lines in the Hansti-Cherani-Friedman book. And otherwise, the paper by Breiman, who are as usual rather cryptic, right? And within very quickly after the start of the internship, Yuansi had done all the things we had envisioned for him. And so the internship went like every week we'd meet with Julia and would think like, what could we ask him to do? Accelerate the algorithm, and then he would get back to us. We had done it. Collect the data sets. We had collected the data set, we had done it, and then he would keep surprising us, just going further and beyond expectations every week. He won the best surprise, we got exactly what he wanted to do. Right. So he won the best research internship award from École Polytechnique, and then he went on to UC Berkeley to do his PhD, where he did many contributions in applications, but also on sampling. And a year ago, everyone was shocked by the fact that he had proved a long-standing conjecture, so the Canal Lovash-Simonovitz conjecture, a very important conjecture on sampling convex bodies that many people had worked on, including many people in this tutor. And Yuansi provided a very elegant and fully rigorous proof without any heuristic argument of this conjecture. So it's such a delight to be here at Yuansi.
Yeah, thank you. Yeah. Thank you, Zaid. Thank you, Armin, for the very nice introduction. Yeah, it's a great honor to speak in this department. Yeah, and also, yeah, I think Zaid helped me, guide me in the initial phase of my research. It's kind of, and it's very important, the first research project you start doing, and that has a lot of influence on your future, and it's really appreciate that. And yeah. So today I'm going to talk about this new work we recently just posted yesterday on arXiv, this localization schemes and the mixing of hit and run algorithm. So this is a joint work with Ronan Eldon. So Ronan Eldon is currently a researcher at Microsoft Research, actually quite close to this university. Yeah, so I'm right now an assistant professor at Duke, and so we are interested in actually establishing rigorous mixing time guarantees or convergence guarantees for MCMC sampling algorithms. Okay, this talk is based on these two papers. One paper is posted about almost 1 year ago, and the other paper is just recently posted on arXiv. So you can see the keyword here is localization schemes. So localization schemes is a kind of an umbrella word for a kind of proof technique that started started from this stochastic localization proof technique. And you can think about this stochastic localization proof technique is like those, it's like this Thor's hammer in a Marvel movie. And it's like a very useful proof technique has proved it's used in like high dimensional probability. And now that like we know how to lift that hammer, and we try to apply this these techniques, try to see how it can help the statistical computing community, like to establish rigorous results. And by statistical community, I mainly mean like the statistical computing community. I mainly mean those MC sampling algorithms. And you can guess from the department I come from that that's what I mean by statistical computing. Okay, so I will first introduce the problem very precisely, and then I will like define this localization schemes rigorously, and then we will see a proof for the mixing time of the hit and run algorithm using those localization schemes. Okay. Okay, so the version of the problem we are sampling problem we are interested in is actually a very simple sampling algorithm. Actually, basically the simplest one you can imagine, but still difficult. So it's a sample from a convex body problem. We want to, well, so we have a convex body. By a convex body K, we mean that it is a compact convex set with a non-empty interior. And this convex body is given, and we want to sample a point uniformly from this convex body. Or in other words, we want to sample from the uniform distribution that is proportional to the indicator on this convex body. So we are going to talk about computational complexity of doing these things. And there are many ways to impose what's the computational model behind it. We'll take an easy one that's just a membership oracle, means that we have access to what we call the membership oracle, that you can ask for any point X here, whether it's inside the convex body or outside the convex body. Every time you ask this question and you get an answer, that counts as 1 unit of computation. Okay. Okay, then we are going to study a particular type of sampling algorithms that's called a hit and run algorithm. So the hit and run algorithm was introduced in the 1980s by Smith. It gets popular actually in the theoretical computer science literature. At each iteration, so it's an iterative sampling algorithm. At each iteration of the algorithm, from the current state U inside the polytope, it will pick a unit vector uniformly on the unit sphere. So it's a random direction theta. Pick this direction theta, and then it will consider the line that is u plus t theta. So in this extend in this direction. So you will draw this line, and this line will hit this convex body in like 2 places. And then you will basically take the intersection between this line and convex body to this segment, and then you sample uniformly from this segment. So then a high dimensional sampling problem to sample a high dimensional problem, we actually only need to sample a 1-dimensional thing, right? Uniformly sample from 1 unit, which is easy to do, especially we have a uniform distribution here. So we get the next point on this. Segment, like a V, and then again we pick a random direction, and then we draw a line and get the next point. V prime, and then you do another direction. So this algorithm iteratively works like this. And people prove that this algorithm has the correct stationary distribution, that the stationary distribution will be the uniform distribution over the convex set. And people are interested in that how fast this algorithm will give you some distribution that is close to the uniform distribution on the convex set. Okay, are there any questions? Yes. That's a good question. So what people do in practice is like, yeah, if you only have membership oracle, you need to get these two points. You do this kind of binary search type of algorithms. So you will have start with very large one that is outside and very small. One point is inside, and then you take the middle point and see whether it's inside or outside, and you do this binary search algorithm until you kind of hit this boundary. And you do it in one direction and you do it in the other direction. Good question. Yeah. Does that will have some computational cost, but usually in this people ignore this type of computational cost. That will be like log on terms of the log of the precision you want to get, but in theoretical study usually people ignore this additional computational cost. Okay, so yeah, so this hit and run algorithm is related to what we are very familiar in statistics, the Gish sampling. So you can consider the coordinate version of a hit and run algorithm where each time the direction you can take is only the axis directions. So each time if you start with U and then each time you can only take this direction or this direction. Say you take this direction, then you sample from this direction, and then you get V, and then you take another direction, you get V prime, and then you get another direction. Then this is like just keep sampling that we use a lot in statistics. Okay, so to quantify the convergence or the how fast we get something that is close to a uniform distribution, we use this mixing time notion. So we look at the distribution. So you start with some initial distribution that could be like a Dirac measure on a point that is inside your convex body. Run an algorithm for k iterations. So this distribution kind of changes. And then you ask the question that after k iterations, what's the total variational distance between your distribution to the target stationary distribution you want? And you want to look for the smallest k such that this distance is smaller than some error threshold epsilon, right? So this is what we call the mixing time. So the theory we want to do is to, given a threshold error tolerance epsilon, given the algorithm, the hit and run algorithm, given some initial distribution, we want to know how many, like what's the mixing time t. We have an upper bound on this mixing time t. Okay. Yeah, so what are the main motivations to study this problem of sampling from convex bodies? So you can think about this as like a prototype of like simplest of sampling problems we can think of. It's actually a very important problem in the computing literature or like theoretical computer science literature, where they want to understand the exact computational complexity for computing the volume of a convex body. So someone gave you a convex body, you want to tell what is the correct computational complexity and what algorithm actually achieve this correct computational complexity for computing the volume of convex body. And actually to compute the volume of convex body exactly, it is known to be a difficult problem. The complexity will depend exponentially on the dimension. However, if you just want to compute the volume approximately up to some epsilon accuracy, people have a polynomial time algorithm to compute it, and those algorithms are based on MCMC sampling algorithms on convex polytope. Also, the sampling algorithms have applications in convex optimization. Like nowadays, people are no longer satisfied with just finding one minimum using gradient descent methods. People are interested in maybe explore the loss surface a little bit more. Like say maybe sometimes you have multiple global minimums. You want to explore the multiple global minimums. Or maybe you want to explore some level sets of all the approximate minimums up to some threshold epsilon, then you take that level set that will give you a convex set in the convex optimization problems. And also the sampling algorithm can have applications just like can be used to build a state-of-the-art optimization algorithms. For example, those cutting point methods that are described in this Liam and Pala survey. Also in Bayesian statistics, we often have truncated Gaussian distributions that arise in Bayesian statistics when you try to use some kind of poor-bit type of model or categorical or some model with categorical variables or sensor data. Those truncated Gaussian distributions arise very often. You can think about the uniform distribution on the convex set is the kind of extreme case of those truncated Gaussian distribution where the variance of Gaussian tend to infinity. Or another way to think about that, we are studying this toy problem to gain some intuition, and many of the proof can generalize to sampling from truncated Gaussian distributions or even truncated log concave distributions. Okay, yeah, just to give you some idea of like this volume computation applications in theoretical computer science is actually a pretty competitive field that people try to get the correct dimension dependency for those algorithms for computing volume. The state of the art algorithm will take like n to the cube, like n is the dimension, n to the cube number of iterations to compute n to the cube iterations of some sampling algorithm to compute the volume, and then there's some per iteration cost. So I think whether this exponent n to the cube can be reduced is still an open question, but I'm not an expert on all this all these techniques that is used here. I just want to show that so it is known that if you can improve some of the mixing analysis there, that can help actually improve the complexity for volume computation. Okay, so we will talk about sampling from a convex body, but talking about sampling from convex body, we cannot skip this very basic algorithm that's called a ball walk. Ball walk is actually even a simpler algorithm than the Hitandrun algorithm. So we have a convex body K. We start from some iteration U. So the proposal distribution will be a uniform ball centered around this U. And then you pick a point in the proposal distribution here. And if this point is inside the convex body, then you accept it. If that point is outside this convex body, you cannot reject it. So this is like very simple algorithm called ball walk, and people study theoretical guarantees for it. And we'll just do a brief comparison of the Hitandrun and ball walk so that to motivate our study. So implementation-wise, there are some differences. The ball walk actually requires you to specify a step size. People know the scaling of the step size, but in practice, just setting the step size is difficult. Well, if you think about Hitandrun, it's like a step size free kind of algorithm. The books, yeah, you need to implement some accept reject step. With the membership oracle, it's not difficult, but yeah, in some cases it might be difficult. And Hitandrun, yeah, here you need to implement this search of these two boundary points that might be trouble in some cases, but yeah. So implementation-wise, they're different, and the key difference being that Hitandrun being an algorithm that does not need to choose your step size. Actually, that's in practice a big advantage. Yes, so this R is yeah, radius, just step size. Yeah, thank you. Yeah, it's the radius here. Okay, and in terms of mixing time, we only talk about the specific type of initialization we call Warmstar. Warmstar just means that the initial distribution and the target distribution, their density ratio is bounded by a constant m. The constant m is a constant here. And then in the case where the convex body has a circumscribed ball and inscribed ball of radii r and capital R and small r, then the mixing time rates for ball walk and hit and run, they match. They are of order n square, capital R square, and small or the over small r square. So yeah, this convex body has a it's not good drawing, but yeah, you find some circumscribed circle and inscribed circle R, and then people establish mixing time for both ball walk and hit and run, and they match. There are another type of assumptions people do. You can assume this convex body is isotropic, meaning that your density that is uniform on this convex body has mean zero and variance identity. So you center the density to zero and rescale it so that its variance is identity. In this case, the mixing time of the ball walk is n square over this isoperimetric constant square. I'll talk about this rigorous later. And in this case, actually, the mixing time of the hit and run is the correct mixing time is unknown, and we can get the upper bound from this first type of assumption, get upper bound here, but it's not going to be optimal. I'm going to show, and the thing is that the main problem we want to solve is just to fill this question mark here. There are other things that hit and run in terms of hit and run has another advantage. It is like it mixes from a cold star. We assume a warm star. From a cold star means that any point in the convex set you can use it as an initialization. It's still a good initialization. Hit and run mixes from that, but this is not a focus on this talk. We'll just talk about the warm star case. And we mentioned this isoperimetric constant or triggers isoperimetric constant psi. It is defined as this way. For a measure mu, the triggers isoperimetric constant is defined as some boundary measure divided by the volume. So if I draw the picture, nu is the uniform distribution over a convex set. Then I partition this set in some arbitrary way into A and A complement. And then I'm looking at the boundary measure. The boundary measure divided by the volume of mu A and mu minimum of mu A and mu A complement. And I'm taking the infimum over all different kind of partitions of the space. So this isoperimetric constant is characterizing whether this measure has some kind of bottleneck. If the measure has some kind of bottleneck, then you can find a partition so that this will be very small. But if the measure doesn't have any bottleneck, then this isoperimetric constant will be large. And the psi n is a quantity people define in this convex geometry. You take the infimum of this psi nu over all isotropic log concave densities, or you can also think about for all isotropic convex bodies. I actually didn't define log concave, so it's like all isotropic uniform distribution on convex bodies in Rn, and you define this quantity, and this quantity is the quantity that appears in the KLS conjecture, Cannon-Lovász-Simonovich conjecture, and this constant for a long time was not known to be like a was not known to be very large, but it's like recent advance that people show that this constant can be bounded of order just log dependent on the dimension. So you can just treat this as a constant if you just don't care about the log factors. Okay, so this observation just says that in the isotropic case, so the Lovász bound is not good enough, meaning that if you try to use this table to fill in this question mark, this result is not good enough when you compare bulwark and Hitandrun. So how do I think about it? So you have an isotropic density, mean zero variance identity. So if I try to apply Chebyshev inequality, I know that most of the mass of this convex body is in the radius square root of n, in the ball of radius square root of n. Also, people know that in the isotropic case, there always a unit ball inside it. So in isotropic cases, you can show that r is less than square root of n, and small r is of order 1. So if you plug in this capital R and small r here, then you get something like n cubed. But if you look at bulwark complexity with the recent advance in the KOS conjecture, then the complexity is only n squared. So yeah, we're asking whether you can get a n squared complexity here for Hitandrun in this scenario. Okay, yes.
Can you compare like this complexity to the complexity of the center of gravity of the convex bodies?
I'm not familiar with that literature actually. Do you know the rates or? A good question. I can do a search after the talk. I'm not familiar, to be honest. Yeah. Yes.
Just a question about the intuition that you gave for the Chigas constant. You said it matters whether the convex body has a bottleneck. So how does a bottleneck for convex body look like?
It's a good question. Yeah. So this isoperimetric constant can be defined for any measures. Yeah, so it can be defined for any measure. So if you have a measure that is like supported onto some weird set with a bottleneck, then it can detect that bottleneck. So yeah, so your question is exactly this Cannon-Lovász kind of conjecture. They are basically saying that for if you look at all the convex bodies where you normalize it to be isotropic, this constant cannot be very small. The conjecture is saying this constant has to be of the other constant. So that's like saying the convex body doesn't have any bottlenecks. So people only be able to prove this. But before all this work, people only be able to prove something like 1 over n to the 1/4, which is much smaller than this constant. Yes. That's a very good question. Yeah, if you know the density, you can probably if you just have the membership oracle, it's actually hard to transform some non-isotropic density to be an isotropic density. So to answer that question, it's like if you are interested in the question, you might want to look into this literature because they are dealing with general convex bodies. And actually, to massage the general convex body to be isotropic, you need to compute its covariance or its variance. To compute that variance, actually, you need a sampling algorithm. So it's like a chicken egg problem. So this type of algorithm usually works like this. Like you do some kind of sampling. You get a rough estimate of the variance, and then you massage your convex body, and then you do another sampling, and then you do this kind of thing. Yeah, it's quite an interesting algorithm there. But it's a very good question that is, in general, we might not get a isotropic convex body, and how to get isotropic convex body. It's like a strong assumption currently. Yeah. Okay, so here comes our main result. So what we show in our paper is that we can show that if the uniform distribution of the convex body is isotropic, then the mixing time of the hit and run algorithm from some Warmstar is this. If this m is of order constant, then the mixing time will be of order n square rather than n cube. Okay, so yeah, so we get a dimension dependency that matches the bulwark, and if we just apply this Lovász 99 kind of work, then we gain a n factor in the mixing time. So yeah, that's looks like a tiny improvement, but it's, yeah, we kind of want to show this result mainly to show that the strength of our proof techniques, and that's going to come up soon. And yeah, a quick glimpse into this Lovász 99 type of proof. Actually, it involves a lot of geometric ideas, and one reason we introduce a new proof technique is that we don't want to get involved into those geometric ideas. And so they use this conductance-based proof. I will describe a little bit in detail later. And you in those conductance-based proofs, you are interested in, like in this convex body, you have 2 points, U and V, they are close. And around U and around V, there's transition distributions that is characterized like from U, you can go any direction with certain probability, and V, we can go any direction with certain probability. And you have 2 transition distributions. And the main thing there is to see how close are these 2 transition distributions. Is like what's the overlap of these 2 transition distributions. And yeah, and then they have to draw this type of like figure where, and they apply some theorems. If you do those high school like geometric courses or like math competitions, you might know those type of algorithms, but those type of theorems. But otherwise, it's kind of quite difficult geometry problem that has to be used there. So this takes us to our contribution. So we try to use what we call localization schemes to as a new proof technique to help prove mixing times of hit and run algorithm. So what are localization schemes? So actually, to be a localization scheme, it's just you just need to have a stochastic process on the measures. So you start with some measure, say uniform measure on the convex set. You just need to define a stochastic process on the measures. So it's like you start with one measure, and then the measure evolves in time, and you get many copies of these measures. And you just need this PT of A fixed measurable set. This PT of A is a martingale. Okay, so any kind of stochastic process on the measures will define the localization scheme. Okay. A specific example is this what we call LDance stochastic localization scheme. It was introduced in this Ronan LDance 2013 paper. At high level, it is a way like to transform a measure, a high-dimensional measure, into simpler ones using a stochastic process or stochastic differential equation that is defined on the measures. The stochastic differential equation is defined this way. PT is a measure. At time 0, it's the original measure. P is a uniform measure. And then you run this stochastic differential equation according to this. What you do is basically you multiply the measure PT by a small linear function. So this dWt is Brownian motion. But if t is kind of if you are in a small time period, this is just a random direction, and you are multiplying this PT by a random direction, a random linear function, and this equation is a pointwise, like defined for all the x's. So this looks scary. Actually, you have an explicit form of this evolution of the density. So you start with the distribution P. The PT has an explicit solution here in this form. It's original distribution P multiplied by some Gaussian density, and then you normalize it, have some normalization factor. When you run this stochastic localization, the quadratic term in the Gaussian is actually a determinist one. The only one that changes is this the determinist one. The only one is random is this intercept, like related to intercept of your Gaussian. And this this CT variable evolves, has a drift term and has a Brownian motion term. So in words, this at time t, your density is multiplied by a Gaussian with variance 1/t. And so when time grows, your density should concentrate more and more. Okay. Well, the center of the Gaussian is random. I will show you a simulation. We did in 2D. We'll not be able to do in high dimension, but in 2D, we did this type of simulation. So we start with this uniform distribution over this convex set in 2D. And then we let this stochastic differential equation run. And here is how it runs. So it's the evolution of the measure. But it's, of course, it's run for one random seed, right? You can do another random seed later. But this is for one random seed. You can see that the measure gets concentrated. And from the equation, you know that the variance is 1/t. So the longer you run it, the smaller the variance is. Okay, then, sorry, this is that I just run the case for seed 126, but I changed another seed. You can see the evolution is slightly different, has a different flavor, and then where the final Gaussian is concentrated at is also a different location, right? So what is important in this stochastic localization process is that the variance of the distribution gets concentrated. You get kind of much simpler, more concentrated distribution, but the location of the center of this Gaussian is changing a lot. It gets kind of more complicated in some sense. Okay, and the location is random. Okay, how do we use this stochastic localization to prove things? So it has been used already in the high dimensional probability, in high dimensional convex geometry literature. So you say you want to show some property of your original density P, but it's kind of difficult to show this property directly. So what you will do, you will transform this density via stochastic localization. You will get all the PTs at some time t, and hopefully that at time t, PT becomes a simpler measure, and you can prove this property A for this simpler measure. And then the final step, you need to relate what you have proved for this simpler measure to the original measure. And since we described this evolution of the process using a stochastic differential equation, then if you are good at stochastic differential equation analysis, you can relate these two parts. Okay, and so this property A can be many things in the high dimensional probability or high dimensional geometry. They were like used for proving isoperimetric inequalities for log concave distributions or isotropic convex bodies that's related to the KOS conjecture. And they were used for proving concentration of Lipschitz functions in Gaussian spaces, noise stability inequalities, or Poincare inequalities in various settings. Now we want to apply this idea to prove mixing time of sampling algorithms, especially the hit-and-run algorithm. So we are going to take a functional inequality approach for proving the mixing time of Markov chains. So that property A is some functional equality that appears in the mixing time proof. And hopefully this property A, this is going to be easier to prove for the transformed measures or for the like those PTs, like for more concentrated measures, it's easier to prove this property A. Okay. Yeah, so the high level picture that in one paper we show is this kind of picture. So one functional equality that you care about in the mixing time proof could be the variance the variance decay. If you are starting with some initial distribution nu0, you apply your transition kernel P iteratively, then at time k plus 1, you get mu k plus 1. And if you can show that at each step, the variance is decaying for any functional P, for any like arbitrary function k f, then you will be able to show that at each step when you apply the Markov kernel, the variance is decaying. So then you accumulate all these k steps, you can show that the variance is decaying at some constant to the power. That's like one functional equality type of proof for proving mixing times. You show the variance is decaying, then you show some chi-square divergence is close to the target distribution. Target chi-square distribution, chi-square divergence of this measure and is close to the target distribution. The trouble is usually this step is when this step becomes difficult, we provide a way to do like things differently. So we will use the localization scheme. We use the localization scheme to transform this measure target distribution mu and also this k-step distribution you obtain from Markov chain. You transform it using some localization. So you have a lot of random measures here, but hopefully those random measures are easier to analyze. And you show the variance decay here. And then you need to relate these two parts. And usually, because we have some kind of stochastic differential equation construction, this bottom part is easy. You show some kind of, this quantity is a super martingale, and then you relate these two quantities. And the upper part is usually the difficult part of the proof. You want to say that the variance with respect to the transform that measure mu t can be related to the variance with respect to original measure mu in some expectation sense. And this approximate, we call this term, this relation approximate conservation of variance. Okay, hopefully you get the high level picture. We will get into a little bit into technical details until we run out of the time. So yes, so we are going to prove the mixing time of hit and run via localization schemes. We will take this conductance approach. The conductance approach is one of the classic approaches to prove mixing time. And the conductance is defined in this way. You are looking at the flow by this transition kernel P, the flow going from a set S to its complement under this measure mu. So this first part, this first part, I can draw this in picture. The mu is a uniform distribution over a convex set. You have a partition of the space into S and S complement, and you are looking at, so at each point of the convex set, the hit and run algorithm transition kernel will tell you what is the mass that is going into the S complement. So basically you are looking at the flow. So like the mass that is going from this side of space, going from this side of space to this side of S complement space in one step of the hit and run algorithms. And you're looking at this flow divided by the minimum of mu S and mu S complement. And yeah, this notion is called conductance. If this conductance can be lower bounded, you will get a mixing time automatically. And in practice, people often use this S conductance variant of conductance. So you will put a minus S here, and you don't consider all S's, just S's that away from 0 and 1. So this allows us to ignore small part of the distribution where the conductance is difficult to bound, and you only concentrate on the most a good part of the distribution. And then this is a classic theorem, says that if you have a S conductance lower bound, you have a mixing time upper bound. So the TV distance can be bounded as a function of the initial like warmness M and this S conductance. So roughly, this says that the mixing time should be roughly 1/phi squared, because this is roughly e to the log of 1 minus phi squared over 2 n, and log of 1 minus is roughly e to the n to the phi squared over 2, right? So the mixing time n you need to make this entire quantity is roughly of order epsilon. You will need n of order 1/phi squared, right? So once you lower bound this S conductance, you get a mixing time of 1/phi squared. Okay, so we described the generic strategy, and the very precise strategy is like this, right? So we don't try to lower bound S conductance directly for the original measure mu. We will transform the measure first, and the way we transform the measure is to use this LDance stochastic localization to transform the measure mu to get a lot of random measures mu t. And we actually run this stochastic localization to time n. N is the dimension of the space. And then we show that for the conductance definition, the numerator of this conductance, this flow going from S to S complement, can be related to the flow going from S to S complement for the transformed measures. And the denominator can also be related, that the minimum of mu S and mu S complement can be related to the minimum of mu TS and mu TS complement. And then in the end, we just need to show that the S conductance of the mu T is can be lower bounded. And yeah, so this is kind of the main kind of inequality in our proof, that you want to show a S conductance for the original measure. So you want to show that this quantity divided by this quantity is lower bounded by a constant, but you don't directly show it. You will first use this super martingale argument to relate this quantity with this quantity that depends on the transformed measure. And then the second step here will be trying to show that for the transformed measure, you can show an S conductance. And then once you show for the transformed measure has the S conductance, you want to relate this part to the original measure, right? So the first step is actually easy to show, that is we have, or at least we have shown it multiple times, just to observe that mu T is a martingale, and usually this quantity will be a super martingale. The second step and the third step is the key challenges in our proof. Basically, we want to show that the transform measure has a good S conductance, and we can relate the transform measure to the original measure this way. Okay, yeah, let me give you kind of some intuition of why it's kind of easier to prove things for the transform measure than prove things for the original measure. The transform measure actually has an explicit form, like I just showed that at time t, it is the original measure multiplied by some Gaussian measure that is very concentrated, right? So where are the centers of this Gaussian, the measure of these Gaussians? It turns out that those CTs has a explicit distribution, or I think it's CT over T. I think the center of this Gaussian is CT over T. Has an explicit distribution when you analyze this stochastic localization or analyze this stochastic differential equation. So the center of those Gaussians will be located very close to your original convex body. And the longer you run it, the longer it is close. So you have your original measure, it's uniform distribution over the convex set. And then you have mu convol with 0, 1 over T. So the center of those Gaussians will be, you convolve it, so it's like a slightly larger measure than the original measure. right? So this will be like your, and then you have this will you have a center here, CT over T, and then you have a Gaussian here, right? So if you draw like most of, what did I say? So the center of this Gaussian will be distributed in this way, so it will be very close to your own original convex body. And the good thing is, like, if your center is exactly inside, very deep inside your convex body, then the convex body boundary doesn't really matter, right? That distribution is the easiest you can imagine. That's just a Gaussian distribution that you want to sample from. But there are some cases where the center is very close to the boundary, then you start to care about the boundary. But our argument is like, I didn't show here. If we run this stochastic localization scheme long enough, here we run to time. Actually, even if you run even long enough, the problem is easier, but you get a worse mixing rate. So you need to choose the correct time so that you stop your stochastic localization, so that most of the mu-t's will be like well concentrated inside this convex body, and in most cases it's easy to analyze the conductance and mixing time of Hitandrun on this Gaussian that is inside your convex body. And there are some difficult cases when it's at the boundary, but there are rare cases that we still deal with, but it's like a smaller number of cases somehow. Anyway, yeah. So I think I'm not going to show all the proof details. Then I'll run out of time. I'll just summarize. So before I summarize, I talk about other localization schemes. So we talked in our paper. We mainly talk about LDance stochastic localization scheme. That is transform your original measure by multiplying it by some well-concentrated Gaussian. And the longer you run, the better concentrated your measure is. But we also introduced other localization schemes that might be useful in some setting. That this is mostly useful in the discrete settings, coordinate by coordinate localization or negative fields localization. For example, this negative fields localization is not multiplying your density by some Gaussian, but it's tilting your discrete measures in some certain directions, and it becomes more and more concentrated in certain directions. And in some cases, it's useful. So there are other results in our first paper. We mainly show mixing time of global dynamics for some discrete measures. They're probably not that interesting for statistic community, but if you're interested, you can take a look at these papers. So in this work, we introduced the localization schemes as a way to prove mixing time. So it is in fact an indirect way of proving things, right? If you cannot show some functional inequality at the beginning, variance decay or entropy decay or conductance for the original Markov chain, you can transform your measure, and maybe after the transformation, it becomes easier to show things, and then you can relate things back. And using this technique, we show that we can get n² mixing time for Hitandrun for sampling uniformly from isotropic convex body. And this is the first result established our technique using localization scheme is the first to establish this rate. And it somehow shows Hitandrun in terms of mixing time is no worse than ball walk. And it actually has a better, easier implementation in the sense that you don't need to choose the step size. So meaning that Hitandrun in many cases, it might be a better algorithm to use. And yeah, that's it for today's talk. If you have any questions, let me know.
Questions?
Does this work analogously for bounding mixing times with respect to other distances? Like if you wanted to bound it in terms of like velocity distance?
That's a very good question. Yeah, so we deal with total variational distance mainly in this paper. It's because like when we deal with this conductance type of framework, yeah, the typical results are shown for total variational distance. So this kind of technique can deal with other distances, but depends on which functional inequality you use for proving mixing times. So if you use those variance decay type of functional inequality or spectral gap type of inequalities, then you prove a result for like chi-square distance. If you use those entropy decay or modify Lobsov inequality type of functional inequality, then you prove a result for KL divergence. For Wasserstein distance, might be possible, but currently I don't have examples actually to, yeah. Thanks. Yeah.
If there are no questions, then let's thank Yuansi again for a wonderful talk.
Thank you.
And yeah, and I guess Yuansi will be around for another hour. Thanks.
Yeah, thank you.
Thanks, Yuansi. Great talk.
So I was wondering, I know this approach for Warmstar-Moonbag transformation to prove, say, CMTs. So that seems to be kind of a similar, I mean, you can also parameterize, I mean, you usually
Yes.
go to the stochastic differential equation expression of the Warmstar-Moonbag process to prove then CMTs, but on high dimension, but I mean, is this kind of related? I mean,
I think it is. I think it is. Yeah.
could
It's
you use this also say to bound the Prohor distance, because that would be more interesting in statistics, right? If I was
to bound what
the
distance?
Prohor, I mean, the basically, or Kolmogorov spin-off distance in one dimension.
Oh yeah, chaos
Yeah,
distance.
yes,
Okay.
or Prohor.
Yeah, yeah.
Can
I
we use that to bound that as well, because it's more interesting in statistics.
okay.
Because
That's
I
a good question.
could
Yeah.
compute critical values, so
What I know,
if I-
people.
So I mean,
Yeah.
if I didn't know distribution mu, I wanted to say bootstrap it. I would want to approximate it somehow. Could one use your results to say, I don't know mu, but I might be able to sample from it, and then I wouldn't be interested in the total variation distance, but something that I can actually use in statistics to compute critical values later to do a hypothesis. So then I would want to look at a different distance, the Prohor distance or the KS distance.
Okay. Yeah, that's an interesting question. I think people definitely relate the classic work that trying to prove Poincare inequality using those OU process or some kind of process. That they consider those kind of thing as a similar proof technique as this. Yeah, but I don't know actually for the KS distance people has done anything. Yeah, that's a very good question, because in our field, yeah, and or in this field, the convex geometry people kind of interested more in those Poincare or like isoparametric. Yeah, but I think, yeah, that's a very good question actually. Yeah.
So you would say the heuristics by your approach works, the stochastic differential equation is similar to why the Ornstein-Wunberg process also is successful.
Yeah, if you look at this survey, actually, I think they might make connection. Oh yeah, this survey, this ICM survey by LDance 2020, it's on his website. They make connections there. Yeah.
Okay, so thanks.
I have a quick question, just a more general question for the isotropic assumption. How robust is it? So if it's like approximately isotropic, right? Do you get like a similar rate with, how close your variance is to the identity? Is it like?
That's a good question. So if it's